I think I see some Citizen Science Club members, which is always great. I'm a big fan of the Cit Sci Club at NC State. Okay, and we are live on YouTube. So just in case you're curious or you're wondering about it later, you will indeed be able to watch this again or share it with your friends. I'll put that in the chat for everybody too. Okay. And I'll pass the mic to my co-host, Deja Perkins, to introduce Make It Count Monday, presented by SciStarter and NC State University. Deja?
Hey, everybody. Welcome to Make It Count Monday. Welcome back, I should say. If it's your first time joining us, welcome. We're so glad to have you here. If you notice, we may have taken a little break, but now we're back, and we hope that you missed us as much as we missed you. And so Make It Count Monday is our weekly live stream show where we talk about citizen science. And this show is a part of the NCSU Citizen Science Campus Program in partnership with SciStarter. So Caroline, do you want to tell us a little bit about SciStarter and how people can find projects?
Yes, definitely. So SciStarter is, and some of you may not have heard of it, some of you might already be SciStarters yourself, starting the science. But SciStarter is a place where you can go and find citizen science projects to do, so real scientific research. And we are privileged to work with NC State so closely. NC State is a citizen science campus. So I'm just going to share my screen really quickly. If you're watching at home or you're watching later, go ahead and type in scistarter.org/NCSU-home. This can kind of be your one stop to get back to the Citizen Science Campus website, to learn more about the Citizen Science Club at NC State, different resources from NC State libraries. But most importantly, it's where you can find real projects to do, including today's featured project, Spirograph. And we're so excited to have our special guest, Patrick Troithart, to tell us, the project leader, to tell us how we can get started, how we can help scientists measure the curvature of spiral arms and galaxies. And there are also the Crowd the Chat projects on this page. If you want to join an investigation of safe drinking water, you can dive a little deeper into sourdough. And each week with Make It Count Monday, we have a different researcher who works with one of these projects explain how you can make your contributions count, how you can make a difference with citizen science. And I know many of you are students, but not all of you are. Anybody from anywhere is welcome to join, to be part of the Wolf Pack with Make It Count Monday, and part of the SciStarter community as well. And this page is a really good place to get you started with tutorial, the projects you can do, and the additional resources from NC State. So I'm going to put the link in the chat. I know I just showed it to you, but I want you all to have it for later. And we also post the recordings of Make It Count Mondays on this page as well. So it's another place where you can find more resources. All right, back to you, Deja.
Thanks, Caroline. So now that we know all about where we can find more citizen science projects, let's get into today's topic. Today, we are talking about galaxies with our special guest, Dr. Patrick Troithart. Doctor, please correct me if I'm saying your last name wrong too, by the way. I am so sorry.
It's Troithart, but that's fine.
Troithart.
Yeah.
My apologies. So he is an astronomer at North Carolina Museum of Natural Sciences. His research deals with understanding the evolution of nearby galaxies by studying their different forms and structures. He is especially interested in spiral galaxies and how their morphology connects to supermassive black holes they harbor in their nucleus, as well as the enormous halo of dark matter they reside in. I had no idea that there was even a morphology to galaxies. So we're going to learn a lot of information today. I can't wait. Dr. Troithart also engages in various forms of science communication and outreach that increases access to astronomy and science in general. I really hope that you all are ready, because today's show is going to be out of this world, literally. And so now, to help me introduce today's topics of galaxies and things in outer space, please put a warm welcome in the chat for our special guest. And to help you all learn a little bit more about him, we're going to do a little icebreaker. Okay, and so this icebreaker is called Inquiring Minds Want to Know. You guys in the audience, y'all are the inquiring minds. So if you have any questions for our guests that you would want to know, drop them in the chat, and then we will go ahead and say them for you. But to get started, I know I'm curious, what exactly does an astronomer do?
Well, I mean, it depends on the astronomer, but basically, it's like any other science. you take data and you analyze data to try to figure out how things work, right? And so specifically what I do is, it seems like it's just a lot of coding. So astronomy can be really broken down into like 3 different branches. There's, the observational astronomy, where you're taking data using a telescope. There's the theoretical astronomy, where you're kind of, running simulations and doing like a lot of math-based things to try to understand, the physics behind what you see. And then there's the like instrumental portion of astronomy, where you're actually building the instruments that go on telescopes that kind of help you, push the boundaries of what's observable. And so a lot of what I do is mostly kind of a mix between observational and theoretical. And so I like to kind of test observations with theory and like, find interesting things that kind of like interesting objects that can then push the boundaries of what a theory can actually predict. So I'd like to touch upon both a little bit.
Very cool. So I want to know, inquiring minds want to know, as a kid, did you ever imagine that you would be working with this project Spirograph, or that you would be working as an astronomer looking at the stars all the time?
I hoped I would be, yeah. I mean, definitely not this project, definitely not galaxies. But yeah, I mean, I was always interested in science as a kid, like all kinds of science. I mean, I loved ants, I loved dinosaurs, I loved space, and it wasn't until like high school when I really started, when you really started doing specific types of science, like, like taking biology classes, taking chemistry classes, taking physics. It wasn't until then that I realized that I really liked physics, and that astronomy was just physics and space, and I was sold after that. So I'm glad I was able to make it this far.
Yeah, so you made the leap from ants to space.
Yeah.
Why study space? Why study this realm beyond Earth?
Just because there are so many weird things in space, like black holes, right? I mean, it's like some of the most extreme things you can think of exist in space, and it's just, and we know almost nothing about it, right? And so even now, like we know that everything that exists in the universe that we are familiar with, so like what we're made out of, what the sun is made out of, everything makes up only about 5% of what exists in the universe. So everything that we can see, touch, taste, smell, that's about 5% of what exists in the universe. 25% of basically 25% of everything in the universe is some kind of matter that has gravity, but we cannot detect it any other way other than through its gravity. So we know something exists because we can feel its gravity, but we have no idea what it is. So we call that dark matter. And then about 70% of the universe is just some kind of mysterious energy that we know even less about. And so really, I mean, everything that we're familiar with makes up about 5% of the universe, and everything else we have no idea about. So it's there's just a lot to uncover.
Yes, that is so true. So you, from what I'm hearing, is that you said, we've discovered so much on Earth already. Let me push the bounds of science and go explore the 95% of stuff we have no idea about. You are a true explorer, I will say that. So the last question I have for our inquiring minds want to know is, what is the craziest fact, either about space or the craziest thing that exists out there, do you think?
I don't know. One thing I've been thinking about recently is that there's lots of crazy stuff in space, and I think just the overall overall substance of the universe, like exactly what's in the universe and how much of it we don't know anything about. I think that just kind of boggles my mind to begin with. But I mean, when we talk about like actual objects in space, I mean, I think one cool thing is that there's predicted to be a region around a black hole where so if you have a light beam that falls in within this radius of around a black hole, it'll basically fall into the black hole and never escape. And if you're outside that radius, that beam of light will actually just bend around it and kind of get arced around the black hole and just continue on its path in a different direction. But there's a specific radius around a black hole where if a light beam comes in, will actually get trapped in the gravitational pull of the black hole and it actually circulate around. And so if you happen to be standing at that radius and you look out forward, you can actually see the back of your own head because that light beam will actually bend all the way around, and the light coming from the back of your head will bend all the way around the black hole, and you'll actually see the back of your own head. So that's called like the photon sphere around a black hole. So it's just weird stuff out in space that can happen.
Wow, that is a pretty mind-blowing fact, if I do say so myself. So, wow, thank you. And so I guess with that, since you've already blown our minds this far, why don't you keep blowing our minds and tell us a little bit more about today's topic?
Sure. So what I'd like to do is actually give you kind of a little bit of background as to what it is that we're doing and why it's kind of important. And so what I'm going to do is I'm going to share my screen, and hopefully I can.
Yep, we see it.
Oh, you do see it? Okay. You see the presentation, or do you see?
We see the presenter view of your slides.
No, okay, hold on.
Deja, I thought of an icebreaker while Patrick's doing that. If I gave you a round trip ticket to outer space, would you do it?
No, I wouldn't.
You wouldn't do it?
Wouldn't. Honestly, I am terrified. I am terrified of the idea of outer space and just being so far away from the ground. Honestly, I have a tiny bit of a fear of heights, and the thought that you could go up that high and then potentially get lost and be out there on your own on a whole new, it's literally a whole new world. So no.
Okay. Patrick, would you do it? Would you take the round trip ticket to outer space? It's round trip. I'm bringing you guys back, but would you take the initial plunge to go to space?
Would I?
Yeah.
I don't know. I mean, I can't even go on roller coasters, and that free fall feeling, it would, I don't know. I think I'd just be puking the entire time. I don't think I could do it.
If anyone wants to put their answer in the chat, I can't believe neither of the guests or my co-hosts, they won't take me up on it. Someone has to go to space with me.
I mean, I want to go to space. I just wish I need like motion sickness tablets or something. I don't know that I could handle it.
You can pack those. That's allowed.
Yeah. Okay. So let me do this briefly because I know we don't have a lot of time. But basically, in space, there are just an enormous amount of galaxies in space. So what you're looking at here, what I'm showing you here, is a very, very tiny region of space that was imaged by the Hubble Space Telescope, and it's such a small region in space. So basically, if you take your arm and you extend it as far, if you extend your arm and extend your pinky and look at your pinky with one eye, your pinky takes up about 1 degree in your field of view. This image is taken of 1/25th of a degree in your field of view. And so this image was taken by the Hubble Space Telescope in what was thought to be an apparently blank section of sky. So what they did was they just opened the shutter on the Hubble Space Telescope and just let light come in, and they just let it expose for a long period of time just to see what was there. So this is basically an exploratory image of empty space, essentially. And so what you're seeing here, every little dot of light that you're seeing in this image is a galaxy. So the Milky Way is a galaxy. We live in the Milky Way. The Milky Way is about 100 to 200,000 light years across. It has 2 to 300 billion stars in it, and so that just kind of gives you a sense of how big a galaxy is. And so every little blip of light that you see in this image is a galaxy. So all these little dots, these little blue dots everywhere, these little red dots everywhere, those are all galaxies. The only thing that's not a galaxy is this right here. That's a star, and that's a star. And that's a star within our own galaxy. So what you're seeing here is about 10,000 galaxies. And if you extrapolate that to the entire universe, the observable universe, we estimate there are between 200 billion to 2 trillion galaxies in the observable universe. So it's ridiculous, right? So anyway, so like in any science, you come across these large numbers of objects, right? And you want to start quantifying, you want to start classifying them, right? So just like you walk into the woods and you see a bunch of green leafy objects, right? You're like, okay, well, we're going to say that these are trees and these are bushes, right? And so you start putting them into bins so you can like make sense of what you're looking at. And so in astronomy, we do the same thing with galaxies. We notice that there are patterns in them, patterns in their shapes, and we start putting them into bins. And so really there are 2 main bins of galaxies. One is ellipticals and one is spirals. So elliptical galaxies are like this one on the left that you see, and it's just a big ball of stars. I mean, again, these are billions of stars, but it's just a giant ball of stars. And if you imagine taking it in your hands and you rotate it, I mean, there's no real structure to it. It kind of looks the same no matter how you rotate it. Spiral galaxies, the ones I'm interested in, are really, really thin objects, in, relative to their diameter. So if you imagine taking two DVDs and stacking them on top of each other, that's the ratio of thickness to basically thickness to diameter of a spiral galaxy. And so what you're seeing here on the right are two spiral galaxies that are, similar, but in that you're looking at one face on, so you're looking at the face of a DVD, and then the other one, the bottom one, is actually the edge of a DVD. And so the bottom one, you can see that it's a very, very thin disk. There's a bulge in the center, and you see that dark line cutting through the center, cutting through that disk region. That's all dust blocking out starlight behind it. And so if you look at the top image, you can actually see the disk-like structure. It forms kind of like a pinwheel. You see those arms. You can see those dark lanes kind of cutting through the arms. That's dust as well in the plane of the galaxy, blocking out starlight. And so here's a very simple classification system of galaxies. It's called the Hubble tuning fork diagram, named after Edwin Hubble. So on the left side, on the stem of the tuning fork, you see ellipticals. They range from circular to hoagie bun shaped to elongated. And then on the right side, where you have the tines of the tuning fork, you see the spiral galaxies. And you notice that there are two main types of spiral galaxies. There are those that basically have a bulge in the center with the arms coming out of it, and then which are along the top there. And on the bottom, you have a bulge. You have the arms, but you also have a linear structure running through the bulge where the arms are coming out of, and those are called barred spiral galaxies. So there are really two main types of spiral galaxies that are non-barred and barred. But you also notice that in these cartoons here, you can see that there seems to be a pattern here in these types of galaxies. So you notice that the ones with the large bulges seem to have really tightly wrapped arms. And the ones with the small bulges seem to have really open arms. And so that's actually pretty interesting. And that's kind of leads into what we're doing. So, all right. So one of the cool things about galaxies is that, sorry if this is flickering. I haven't figured out why it does that. But what you're looking at here, these are, on the left is a cartoon video of stars orbiting around an unseen object. And on the right is actual data of stars orbiting around an unseen object within our own galaxy, within the Milky Way. And these are stars near the center of our Milky Way. And what the object that these stars are orbiting around is a black hole about 4 million times the mass of the sun. And what we know is that every galaxy we look at, not only the Milky Way, but other galaxies we look at, they all tend to have what's known as a supermassive black hole in their nucleus, within the bulge of the galaxy. So deep down inside the bulge of a galaxy, there's a nucleus, and in that nucleus is what's known as a supermassive black hole that ranges from millions to billions of times the mass of the sun. And this is in basically every single galaxy we look at. So the question is, how do we get these things? Why do they exist in the centers of galaxies? One thing we know is that as a galaxy evolves, so we can look back far enough in time and we can see some of the earliest galaxies. And we have evidence that these supermassive black holes exist already that far back in time, like when galaxies are basically first kind of born. And so it's unclear how galaxies can form supermassive black holes so quickly after the galaxy is kind of formed. So somehow, as a galaxy is being born and kind of evolving with time, so does the supermassive black hole that's in its nucleus. And so it's not clear how you can form something that big that quickly. So there are competing ideas as to how that can happen. So one is that you can have, this is maybe getting into the details, but one idea is that you can have giant gas clouds in the center of a galaxy that just kind of collapse under their own gravity and immediately form kind of the seeds for supermassive black holes that then, these seed black holes kind of merge together very quickly and form a supermassive black hole. The other idea is that maybe stars go supernova very, very quickly near the center of a galaxy, form what's known as stellar mass black holes that range from, hundreds of to thousands of times the mass of the sun. And then all those kind of coalesce together very quickly and form a supermassive black hole. So we don't really know. But one key is to maybe finding these types of black holes that range between the stellar mass and the supermassive, what's known as intermediate mass black holes. The thing is, we haven't seen many of these. There may be a dozen candidates and maybe 2 or 3 confirmed cases of intermediate mass black holes. So we really don't know that much about them, or really if they exist. But if we can find a lot of them or more of them, we can kind of determine what causes intermediate mass black holes to form and why they didn't become supermassive black holes. What in their environment stopped them from growing and becoming much larger. So one of the goals of this project is to hopefully be able to find these intermediate mass black holes or find candidates for intermediate mass black holes, so that way we can follow up and confirm that they're intermediate mass, find all those cases where those happen and see what the common thing is between all of those galaxies that stop the black holes from growing to becoming supermassive. So maybe there's something in the environment of these galaxies that can tell us, what stopped that growth. So maybe there wasn't enough gas in the center of the galaxy to make them grow or something. We don't know. So one of the cool things is that we can estimate the mass of the black hole in the center of a galaxy through kind of a simple process. And so what we can do, so there was a paper published that saw that there seems to be a correlation between how tightly wrapped the arms are in a spiral galaxy and the mass of the supermassive black hole. So if the arms are very tightly wrapped, the black hole mass should be large. If the arms are very open, the black hole mass should be small. And so what everybody's been finding is galaxies on this end of this cartoon diagram here. So in the blue dotted area or blue dashed area. So here we find all these supermassive black holes. What we're hoping through this project that we developed is to maybe be able to find some black holes that fall on this lower end of this plot. And then those might indicate that there are intermediate mass black holes in those galaxies. So this is a really simple method of measuring black hole or estimating black hole mass. Rather than spending a lot of telescope time on a galaxy, we can look at photographs, measure how tightly wrapped the arms are, and kind of get an estimate. The issue is that a lot of these photographs aren't fantastic. So this is an example of a spiral galaxy, and you can see in this image, there's not a lot of contrast, right? You can't really, it just looks like a blob, essentially. But if you pay really close attention, if you kind of tilt your head, look at your screen a little bit, you can see that there's some spiral structure in there, right? You can see hints of spiral arms. You can see hints of gaps between arms, right? So if you plug this image into into a computer program to measure spiral structure, it's really not going to be able to do anything. It can't see where the arms are. It can't see where the interarm regions are because the contrast is so low. But people are really good at seeing patterns. I mean, that's basically what the human brain is designed to do, is to find patterns. And so what we wanted to do was take advantage of people's innate ability to see patterns to kind of show us where the spiral structure is in galaxies. So that way we don't have to rely on the image. We can rely on what people show us and measure that. And so this is just a little schematic diagram of the idea of what we wanted to do. So we would show people an image of a galaxy. We would have them trace out where the spiral structure is, and then we just throw away the image. We don't need the image anymore. We can just use their tracings and then measure their tracings. And so we essentially increase the signal to noise ratio of the spiral arms and are able to measure that, pretty accurately. And so from that, we developed our project, which is Spiral Graph. And so so that's kind of the background. So I guess I'll leave it there, and we can continue on with, we can actually move into what we want to show with the actual project if we want.
Yeah, I think that's great. Thank you so much for giving us that background information. I know I knew absolutely nothing about outer space and galaxies before this. One of those diagrams, I vaguely remember maybe seeing that as a kid, maybe in high school as we were going through like our biology book or something, but that's about as far my knowledge of a galaxy goes. And I had no idea that galaxies look like a bunch of jewels when you take pictures of them. That's pretty amazing. So you just might change my mind about going into outer space. Just maybe. All right, so now that we have, talked a little bit about the project, do we want to go ahead and do a project demo and figure out if we can indeed be on the forefront of a lot of these discoveries and assist with this data collection?
Sure. Yeah, we can do that. So let me share the screen here. All right. So this is the page for Spiral Graph. This is the home page. So you can just navigate to either scistarter.org/spiral-graph, or you can go to zooniverse.org where it's hosted, but the URL is a little bit longer. But yeah, but it's pretty easy. You can just go to get started, and so actually I'm logged in, so it actually knows who I am. But generally, if you've never been here before, a tutorial will pop up, and it just kind of takes you through, what you're looking for, what to ignore, things like that. But I'll walk you through that so we don't have to actually look at the tutorial. But what we do is we show you a picture of a galaxy, and what you're interested in is the object in the center of the image here. So sometimes there'll be other galaxies in the field. Maybe there'll be like a large galaxy kind of off to the right hand side. You want to ignore all of that. You want to focus on the object at the dead center of the image. That's the object that we're interested in. And so the first thing we do is we just want to, so all of these objects should be spiral galaxies. But what we've been noticing, or when we first kind of launched this project and started looking at the images and things like that, we noticed that not all of them really were spiral galaxies. There were cases where some of them were elliptical. Some of them were merging galaxies. So it's maybe like two spirals merging together and scattering stars and things all over the place. So that you couldn't really get a sense of the spiral structure that was originally there. They were too distorted to actually see the spiral structure that kind of developed over time as the galaxy slowly evolved on its own. And so what we do is we ask you, is what you're looking at a spiral galaxy that basically, is it a galaxy that looks like it has structure, which would imply a spiral galaxy, and does it have and you want to make sure that it doesn't look like it's interacting with another galaxy, that it's not obvious that it's being distorted by a nearby galaxy, and it's the nearby galaxy is pulling on it, or it's collided with another galaxy, or done something strange to distort the spiral arms in the galaxy. And so the first thing we do is we just ask you if it's a viable spiral galaxy or if it's not. And in this case, I would say this is a good spiral galaxy. So it looks very regular. It doesn't look like it's being pulled on by anything. It's in the center of the image. This is the one we're looking at. So I think this one's good. And so one thing I like to do just for myself is I find it easier to look at negative images to see black on white rather than white on black. And so you can click the little image flip icon down here. And so you can see the spiral structure here. You can see the image. You can actually also zoom in on it as well to get a better look at it. So this galaxy is not merging with anything else, and it looks structured, which means it's spiral. So I'm going to select that and click next. And then we just ask you to trace out the spiral structure that you see. So you just click one of these trace icons here. And what we ask is that you just trace out the spiral structure you're comfortable with that you can comfortably see. So we want to ignore the bulge of the galaxy. We want to ignore the bar of a galaxy. Sometimes these barred galaxies will have rings surrounding them. So kind of oval or, kind of continuous rings that surround them. And then you have arms coming out of these rings. So you want to ignore the rings as well. So for instance, in this case, you see there's a bulge right here. There's kind of a fuzzy, I would say kind of a pseudo ring region right here, but I can see the arms right here. So what I'm going to do is I'm going to trace out, oops, oh, I just screwed that up. So I'm going to start again. So I'm going to trace out this arm right here. And I think it kind of wraps around like this. And then I'm going to trace a second arm, which looks like it's right here. and that's it. And so you can either click, done and talk. So if you want to talk about this galaxy with other people, you want to mention something, you want to tag it as something, or you find something weird in the field of view or the galaxy itself, you can talk about it there, or you can just click done. And what'll happen is it'll just show you another galaxy. So this one's actually pretty interesting looking. This one's actually pretty cool. But yeah, that's basically it. And so if you pick smooth, merging, or untraceable, so what that means is, the galaxy's off center, the galaxy's actually an elliptical, it seems to be merging with something else. If there's something just basically wrong with the galaxy, you click that and it'll just show you another galaxy. It'll just bring up another galaxy. And so it's really easy to go through this. I mean, you could, once you really get into it, you do maybe 5 of them, you could probably do like one in less than a minute. And so we've been getting a lot of people doing a lot of galaxies.
I actually want to see how good our audience is at picking out these galaxies. So if we could, for this one, if you can share, vote, exactly. Caroline said it in the chat, vote in the chat. I want to know, how many arms does everyone see? And then I want you to tell us if we're right or wrong.
No, okay. Well, I'm going to say for sure that this is structured not. This is a good example.
Okay. So I see one person says 6 and that this one is weird. I will agree with you, but I like that you can tell that this one has arms. There were some that I've gone through while trying to do the project, and I couldn't tell if it had arms, like if it was structured or not structured. It was pretty rough. Mm-hmm. So someone says 6. I took a guess and said 5, but I felt like 5 was pushing it.
Yeah. I mean, but so again, galaxies are like flakes, right? So you can't. The arm structure isn't, totally regular sometimes, and so let me show you an example here. So if you look, so I'll trace out this arm here, and so you can see that once you get here, the arm kind of splits, right? So it kind of bifurcates, and so you can see that there's an arm that kind of continues on this way. Something like that. But then also, it looks like there's an arm that kind of continues out here like this from that initial arm. So, and this is perfectly fine. If you want to trace it like this too, that's perfectly fine. So you don't, you just want to trace, everything that you feel, as much as you feel comfortable with. So I don't know. So, I mean, there's like an arm here too, doing something like this.
What happens if we're wrong? So if we trace something incorrectly?
Well, if you know that you're wrong, you can just click on the arm. So for instance, let's say I screwed up this yellow one. Sorry, it's not working really fast here. So you can click that and you can actually, so I screwed up there. So you can just click on them and you'll get the X, which you can just click to eliminate your tracings if you need to start over. So you can do that. But overall, like if you don't, if you traced it as best you can and you think you did it right, but that's fine. That's exactly what we want you to do. But you're not tracing it. You're not the only one tracing each galaxy. So there are going to be 14 other people tracing the same image. And so what we do is then we aggregate everybody's tracings and we use, basically the wisdom of the crowd, right? So we compare what everybody else does, and where people overlap, that creates a stronger signal for us, and where people disagree, that creates a weaker signal. And so we're actually working through the statistics right now of, how much agreement do we need to actually count that. And what we've been seeing is that generally people agree really well with a lot of these arms. They're only like, you get a few kind of straggler tracings and things like that. And so one thing we do for sure is we eliminate where there's just, a single tracing where nobody else agrees with, we kind of eliminate those sections of the tracing. So if you have just, like for instance, if I end up tracing, you know, this arm going like way out here like this, nobody else is going to follow that. And so somebody may follow the arm out here. So the section of arm that will correspond with other people will agree, but then all this part out here will actually eliminate because nobody else agrees with it. So that's one thing we've been working on and trying to determine how much agreement we actually need to call it good. And definitely where nobody else agrees with somebody, we eliminate that.
I'm really glad you asked that question, Caroline, because I think sometimes, I don't know if people maybe forget that citizen science projects are contributing to real data, you're contributing to real science projects, you know, people are using this for real research. So I think for me, sometimes I get a little bit nervous thinking that, oh, if I mess up, I might be ruining this entire project. But it's really great to know that, you know, agreement leads to the classification, and it takes some of the stress off of the participant, definitely.
Right. Yeah. Yeah. I mean, if you do your best, I think you'll be fine.
All right. So I will say, do you agree with the folks in the chat that there are 6 arms here?
Yeah.
I know we traced 3.
1, 2, 3, 4. Man, 5. I would say there were about 6. I mean, it could even be more because they kind of split off out here at the ends too. So there could be like little arm fragments coming out too. So yeah, it could even be more than 6. So some of these are have much clearer examples than others. What's known as grand design galaxies that are essentially, you know, very, very obvious, very strong arms, and generally like 2-armed galaxies that are very, very strong arms. And so you'll occasionally run into those as well.
Now we have a really hard question. Oh, sorry. I think I'm hearing an echo. Okay. Sorry about that, everyone. Thanks for being patient with our technical difficulties. It's just part of the live stream life. But Deja's laughing because she knows she saw the same question come through in the chat. They want to know, is my background traced correctly?
Yeah, because I actually traced that. Yeah, that's the spirograph logo, and I picked a pretty famous galaxy from this is a Hubble image of a very famous galaxy called the Whirlpool Galaxy, and yeah, so I ended up tracing that and making that the logo.
Oh, okay, very good. Yeah, I knew it was. I just grabbed the main image on the SciStarter project page, and I chose well, so that was good.
Yeah.
Deja, do you have any other questions after our demo? I feel very educated now. It's helping me become a better spirographer.
I do. I agree with you there. I know the first time I went through the spirograph project, I did it with a few other students, and they were really spot on and able to identify those arms. And I was the one with a lot of the self-doubt and not being able to recognize them. But I feel like after our practice today, I would feel super confident doing this by myself. And so actually, we have a question in the chat that I want to address really quick before we move on to talking about the actual data. And that is, someone asked, do participants get to see how well they are doing in terms of consensus with other participants? It's a good question.
Yeah, that's a good question. So yeah, unfortunately, we can't do that because the way that Zooniverse is set up, you can't kind of look at data on the fly. You have to download. You have to request and then download your classifications. And so we can't really do it on the fly. We can't compare your data to other people's data on the fly. So unfortunately we can't do that. And it's possible. I mean, theoretically it's possible to do, but it would take some time to build and like some immense processing power to kind of collate everything and then show it to you in a reasonable amount of time. And not to mention also requesting, constantly requesting the data from Zooniverse. It's not instantaneous either. And right now our files are gigabytes. So our classification data that we download is like gigabytes. So it takes a while to download each time. So we only download data about once a month.
So, going along those lines of data, if you download it once a month, about how much data do you have every month? I mean, can you gauge how many participants you have for the project monthly?
Yeah. So yeah, so actually, so our project, so one thing I've done with this project is I've created a monthly leaderboard, just to give people a sense of, how much people are classifying, some, I like to be able to recognize people who contribute a lot. And so every month I create like a top 5 list just to recognize the people who contributed the most. And then I also, in that leaderboard post, I also talk about, the status of the project and what we're doing and things like that. But yeah, we have, each month we have, you know, I would say at least 100 different volunteers working on it, if not hundreds. I mean, right now we have over 6,000, we have 6,500 registered volunteers on the project. Obviously not all of them are active all the time. But I mean, there's some people who are incredibly active. I mean, there are volunteers who have, classified thousands of galaxies, and I mean, like, 7,000 galaxies or more. I think there's one volunteer who's approaching 10,000. So if not exceeded it, I can't remember now. But yeah, I mean, there are definitely people who thankfully participate a lot in this project, who provide a lot of data, and that's really fantastic. But even if you contribute, a couple galaxies, I mean, even that is helpful. I mean, we don't want one person classifying everything. We don't want to bias all the tracings to one person. So, you contributing, a few helps, because it adds diversity to the overall tracings of the galaxy. So not all comes from one person. We get a nice mix of input from different people.
That's really great to hear. And so, what would you say your primary user group is like? What does your community look like? Who can participate in this project, I guess?
Well, I mean, I think it's mostly geared to kind of middle school students and up. So when we were building this project, we tested it out in the museum, and just kind of had people off the floor just, test it out to see if they were interested in it, and how they were able to contribute to it. And what we kind of realized was, it was just, there's a level to it where, there's a level of patience to it, because, obviously you're looking at hard to interpret images, and just sitting there and kind of clicking point to point, and so I think small children have a harder time with it, just because in general, small children are a little less patient. But I feel as people get older, they have a little more patience and a little more, a little more focus, and they can do it. So I think ideally it's geared toward middle school and up. And I know, a school teacher in Tennessee actually reached out to me through Twitter, because they were actually actively working on the project. And I think it was a middle school teacher who showed it to their students, and they were actively working on it one afternoon, and were kind of chatting with me about it. So it was pretty cool.
That's awesome. I would be curious to know if there was a sweet spot with your user groups because, are the eyes of middle schoolers better than the eyes of, some 20 somethings, 30 somethings, the rest of your user groups? I think that'd be pretty interesting to know, like who are the best galaxy drawers out there who can draw
Right.
these arms the best.
Right. Yeah. Oh man, I wish we could know that. Yeah, I don't know. Yeah, because we unfortunately we don't collect ages. I think if you log into SciStarter, I think if you create a SciStarter account, you can input your age into your SciStarter account, but I don't think many people do that.
Yeah, it's always optional. And that's actually a really good segue. We'll go over this again at the end, but if you go through that NCSU homepage I showed you all at the beginning, and you follow the directions on the spirograph like subpage on that page, you'll be able to track the number and frequency of your contributions to spirograph in your SciStarter dashboard just by inputting your Zooniverse username. So that helps us. We understand how well NC State is doing in the wider NCSU community compared to the rest of the citizen science ecosystem, and allows us to give you all credit for your collective impact. And Deja, I love that you asked that question, because I know we have a few Citizen Science Club members in the room with us tonight. Take that as a challenge. We don't necessarily have that leaderboard, but if you all are the best, we'll know. We'll be able to see it on SciStarter.
Yeah, so don't let the fact that someone has almost classified 10,000 galaxies deter you from participating in this project. We still need your help. And I guess one question that I'm, curious about is somebody has contributed 10,000 galaxies. So where are you all, I guess, in the process of with the data? I mean, do you foresee you all being complete at any point, or how does that work?
Yeah, so we actually have two kind of data sets that we were analyzing. The first was a set of about 6,000 galaxies, and the second was a set of about 14,000 galaxies. And so the set of 6,000, we're actually done collecting data with. So we're now in the set of 14,000, and we're actually near the end of the 14,000 galaxies right now. So we only have about 5,000 galaxies left in the 14,000 that we're classifying. And then once they're done, we anticipate, so we need to check the data to make sure that we have enough independent classifications. But I anticipate that we'll have that. And if that's the case, then actually the spiral graph project, the data collection portion of the spiral graph project, will actually go into hibernation until we can get more data. And so our project is actually based off of data collected by another citizen science project named Galaxy Zoo. And what Galaxy Zoo does is they look at images of galaxies in the sky that are totally unclassified. So it's unknown if they're ellipticals or spirals or mergers or whatever. And so volunteers in Galaxy Zoo actually classify these galaxies as to what they are. And so what we do is we take published data from Galaxy Zoo, pick out the ones that are likely spiral galaxies in order to trace those. But again, what we've noticed is that some of these classifications are not entirely, it's a probability of these being spiral galaxies. And so some of these we've noticed that some of these aren't spiral galaxies that we can use. And so that's why we ask people again, is this really a spiral galaxy? Is this a traceable spiral galaxy? Ideally they should all be. And so we wouldn't even have to ask that question, but we've noticed that some of them aren't. And so that's why we ask that question before we have you start tracing them. But so anyway, so the point is that Galaxy Zoo is still running, and they're running on a new section on some new data that hasn't been observed in that, it's a sky survey of galaxies, it's basically a sky survey with galaxies in the survey. But it's a new section of sky essentially. And these galaxies haven't been classified yet. And so once Galaxy Zoo has finished classifying these galaxies, we can then pull out those spirals from that new section of sky, and then we can continue on with our project with a new sample set. But we're waiting for Galaxy Zoo, and I don't know how long that would take to get them for those galaxies to be done. But once they are, then we'll take it out of hibernation and try to generate some more data. But we already have 20,000 galaxies that we're working on. So we're in the process of analyzing the first batch, and then we're going to analyze the second batch, and then maybe by then Galaxy Zoo will have published their data, and we can restart the actual data collection in spiral graph rather than just the data analysis.
All right, so I'm hearing a few things. I'm hearing that everybody in the audience needs to hurry up and participate in Spiral Graph before they run out of, so we can get those 5,000 galaxies classified. And then I'm hearing participate in Galaxy Zoo so that you can explore the unknown and classify more galaxies. So we have even more things to classify for Spiral Graph. So you got a 2-for-1 this episode. 2 different citizen science projects that you can participate in that are about, galaxies and the stars and all the things beyond Earth. So I'm just wondering, since we were, talking about everything related to, you told us that story about, the other user groups and people who can participate. And I'm just wondering, are there any curriculum materials or things that educators could use in order to bring spiral graph into the classroom?
Yeah, so we actually developed, so I can actually show you that. So we developed a set of like learning modules for the project. So if you go to about and then education, we created a set of, learning modules about galaxies. So just really, what is a galaxy? You know, where does the term galaxy come from? It's kind of the history of galaxies, things like that. So that was module 1, and what that is, these modules are just Google slideshows that you can view and download. And then in the slideshow, the last slide actually takes you to a Kahoot quiz, like a 5-question Kahoot quiz, so you can test your understanding at the end of each one of these modules of, you know, for the concepts that we threw in there. So the second module talks about the different types of galaxies. So like I talked about with the ellipticals and spirals and things like that. And then it relates to spiral graph. And then module 3 talks about how we think galaxies form. So the origins of galaxies and things like that. So we try to create kind of a comprehensive, like, galaxy learning framework, I guess. To at least, you know, if teachers don't want to use it or students don't really want to use it, at least it's some background information for volunteers who come to the project and want to learn a little bit more about galaxies. They can go through the slideshows and just kind of pick up some more information if they want.
And so I guess along that lines, what I've been learning recently as I've been working with our Crowd the Tap project, that a lot of these teachers want access to the data sets so that their students can, you know, analyze things and come to their own conclusions, do their own research projects. Are there any data sets that teachers can access and have their students look at?
Yeah, we haven't made those public yet because we're still kind of collating everything, and you know, we're making the aggregate images and trying to analyze them and like remove the noise, you know, remove the, you know, the random tracings, the one-off tracings. But the idea is that once we've got the data in a format and we're done analyzing it, where everything is going to be public, and that you know, we're gonna, the goal is to create a giant database that anybody can access that will have the galaxy images, all the metadata for the galaxies that we've had, plus the tracing images. So we'll include the individual tracings plus the aggregate tracings, so that people can have access to, so they can compare, you know, so they can look at the tracing results compared to the actual images. And then, you know, the software we use, that's freely available. We've developed that and made that public. So that's the software we use to actually measure the curvature of the spiral arms. And that's freely available. You can find that on the Spiral Graph website. There are links to it there. And then, you know, so if people want to, you know, come to their own conclusions, measure the data themselves, they can definitely do that if they want. Yeah.
Awesome. That's great to know. So we only have a few more minutes left in our program tonight, and I do want to open up the floor and give the audience time to ask questions if they would like to. So, you know, if you are in the audience tonight and you've had a question that's been burning on the edge of your brain all night, here's your chance to step up to the mic and let us know. So if you have a question, Caroline, do you want to let them know what they can do?
Yeah, you can use the raise your hand function and I can give you audio or video. And if you're shy, you can write it in the chat. We won't force you to go on audio or video, but it's a new thing we're trying just to give people a chance to make their voice heard. So while I wait for people to raise their hands and or put their questions in the chat, one big thing that's on my mind, I've been looking at these pictures when I'm participating in Spiral Graph, and it makes me think, like, could Spiral Graph have existed like 10, 15 years ago? Or what technologies have enabled this project?
Well, I think the digital images are key in that, you know, doing this with photographic plates, for instance, I think that would make things more difficult. I mean, to be honest, like you know, even through graduate school, like everything that I've learned has all been digital. So I can't imagine, you know, going way back to, you know, pre-digital to do any of this. I mean, it's just, I don't even know how you do it.
Maybe by correspondence. Could you have mailed everyone the pictures and they could have physically drawn them?
Oh man, yeah. Oh, that would be so difficult and so time consuming.
Yeah. And wow, a lot to think about there. Yeah. Deja, do you have any more questions? Oh, what were you gonna say?
No, but I mean, one of the good things about doing this, like in today's age too, is that, you know, artificial intelligence is coming to the forefront now too. So there's like machine learning and computer vision, things like that. And so really one of the goals of this project as well is once we've collected all this data, we now have the original images and we have good approximations as to where the spiral arms are in the galaxies based on what people have seen. And so what we can do is we can take those tracings and use that as input into an artificial intelligence program, essentially a machine learning program, to train the machine learning program to find the spiral structure in the images. And then we can take a subsample of those tracings, use that to train an AI, and then have it measure the rest of the images. And then we can compare the AI's results to what people have actually done to see how correct it is. And we can keep training it until it actually does it correctly. And so one of the goals is hopefully we can use the data that people provide to actually create an AI where we don't need the people anymore. So hopefully the AI can be good enough that it can just do it automatically and we don't actually need people to recognize the patterns anymore. Maybe the AI can actually see the patterns by itself. And maybe we just need the people to say, yes, this is right, or no, this isn't right. And we have the AI do it again or something.
Would that make the project more efficient? Maybe you'd be able to accomplish even more research by focusing people on the tasks where you really, really need them. Or what would be the future for citizen science in that context?
I think there's still the need for citizen science, but I think it's less. I think it's more of checking the work rather than doing the work, because you can let the AI actually do the work, and then you can just have people check it and say, yeah, that's right, or no, that's wrong, and then, just so that way you can actually pull out the good data from the bad, and not have to wait for people to, you don't have to wait for 15 people to look at a galaxy. You can just have 15 people look at a galaxy. You could have a person or two people or three people just look at the results and say, yeah, that's right, or that's wrong, which is significantly faster than actually tracing an image.
Deja, do you have any more questions? Or
I mean, not really. I was just going to say, you guys should really hurry up and participate in this project before the computers take over and, no one can participate anymore. You just be looking at the galaxies for fun, or like double checking your computer's work and, just so participate in Spirograph. And I guess with that really wraps up our show for today. I would like to pass the mic over to Caroline if you have anything else that you want to share with us really quickly before we wrap up.
Yes, don't forget everybody. And also there are new frontiers, we'll keep on participating. And I saw in the chat, someone said, no, computers can never be smarter than people. I think the computers will be our friends, and we'll work in collaboration with them to discover new things. But you can go to Spirograph here on the NCSU homepage. You can read the instructions and click that participate button, and the tutorials linked here, and some other resources. I know a lot of instructors or educators will print these out and literally give it to their students if they need a handout. Some people are more visual learners, and that's totally great as well. But one key instruction here about getting credit for your SciStarter contributions is in your SciStarter dashboard info and settings. So this is mine. I have my Zooniverse username entered, Caroline Hewitt Nickerson, and I'm able to track the number and frequency of my contributions in my dashboard. And because I'm listed as, there, I have 427. I'm able to see, if I go through it, my stats for Spirograph. So we really encourage you all to do that so we can include you as part of it. And somebody raised their hand. I'm going to promote them to panelists so they can ask a question. So exciting. We have 1 minute left. You came in just in time.
Oh, hello? Oh, hey, sorry guys. My house might be a little loud,
no,
but
this is perfect. This is perfect. Thank you so much for joining us.
Oh yeah, pleasure. I'm Patrick as well. So anyways, but so I was wondering what your best theory was for like why these, I guess, massive black holes have, like, did you say that they were sparse or spread out? I kind of forget now, but these galaxies with the
those you mean the black holes in the centers of galaxies?
Yeah, so as the black holes in the center of galaxies are more massive, you said that the arms are like spread out more, right? Or more tight.
Yeah, they're more tight.
Yeah, they're more tight. So is that, so I know like if it was just more massive or more dense, it'd become more tight, like just as an object, but do you think there's something else going on?
Right. Well, so yeah, so it seems, yeah. So intuitively that would make sense, right? You'd expect like a more massive object to kind of pull things tighter together, right? But the issue is that the supermassive black hole in the nucleus of a galaxy, even though it's millions to billions of times the mass of the sun, compared to the size of the galaxy, it basically doesn't exist. Like the arms in no way should actually feel the influence of the supermassive black hole. So really what's happening is there's actually a ladder of things that go on as you get further and further away from the black hole. So the supermassive black hole, like we saw in that video, affects kind of the stars nearby it, right? So really the supermassive black hole affects the region, just surrounding it, very closely surrounding it. And then that region actually affects the rest of the stars kind of in the bulge, right? So what'll happen is if you have a supermassive black hole, so there's a really well-known correlation between the mass of the supermassive black hole and the mass of the bulge of a galaxy. So like the size of the bulge of a galaxy. And so if we go back to that Hubble tuning fork diagram, the ones with really tightly wrapped arms actually have large bulges, and the ones with open arms actually have small bulges. And it's really that bulge supermassive black hole relationship that's really tightly correlated together. And then the bulge and the arm winding is correlated to, or seems to be correlated to each other. So it's really the arms correlate to the bulge correlates to the region around the black hole, the region around the black hole correlates to the mass.
So, okay, so just to get this right then, so you would probably think that somehow the black hole forms and then that causes the bulge to form and the bulge causes the arms to.
I don't think I think somehow they co-evolve. I don't think one is dependent on the other. I think the galaxy forms and then the structures evolve very quickly to match what we see now. In that, you end up with a supermassive black hole and a bulge, but the effect of the supermassive black hole will affect, maybe the bulge starts out small, but then it'll get bigger because of the effect of the supermassive black hole. And as that bulge gets bigger, then the arms, maybe they're loosely wrapped and then they start to become more tightly wrapped over time, things like that. So I think if you go back in time and look at these galaxies, I don't think the arm wrapping relationship with the black hole mass would really hold as you go really far back in time, because I think it hasn't reached equilibrium yet. But we're looking at galaxies like closer to now. We're looking at nearby galaxies, and so that relationship has had a chance to settle.
Okay, thank you. That was awesome.
Yeah.
Thank you so much for joining us and hopping on and asking your question, Patrick. And I have one more question before we hop off. I know we're already over time, but I just got inspired after hearing that last question. What happens when galaxies collide? I've been wanting to know all episode.
Yeah. So it's pretty amazing. I mean, it's really, it can be really beautiful. I mean, we have plenty of images of galaxies, in different times of collision. So like we see them post collision, we see them pre-collision, we see them during collisions. But basically what happens is, so galaxies are mostly empty space. I mean, even though they look like they're, densely packed stars and things like that, they're essentially mostly empty space. So the distances between stars is vast, even in a galaxy, even though they look like they're very close together. There's vast distances between stars. But the gas clouds within galaxies are very, very large compared to the separations. And so if two galaxies collide, really what happens is you have like the gas clouds within the galaxies colliding with each other, and then they'll kind of shock and form new stars. So you end up with like a lot of star formation. A lot of blue stars will form in like the shock zones. But all the stars that already exist will kind of just get scattered all over the place. So they'll feel each other's gravity, but they won't necessarily collide with each other. They'll just be scattered all over the place. And so that's why you get like, if you Google like merging galaxies, you'll just see arms kind of like strewn about in space, just kind of, just launching stars into space. And so you just see, you just see kind of like like grains of sand scattered on a beach blanket or something. You know, you just see stars kind of scattered all over the place. But the gas clouds, when they collide, you'll actually see like kind of strings of star formation there.
You know, I think that is exactly what I'm going to do. As soon as we log off of here, I'm going to look up galaxies colliding so I can see some of those really cool photos.
Yeah.
But I do want to just say thank you so much for joining us today. And thank you for sharing your knowledge. Thank you all out in the audience for tuning in to another episode of Make It Count Monday. Join us next week as we talk about Coco Ross with our guest, Sean Hauser. If you are an NC State student interested in citizen science, consider joining the Citizen Science Club, where they will go and do a ton of more citizen science projects. So if you've been hooked by this episode, go ahead and join the Citizen Science Club. And a special thanks to NCSU Citizen Science Campus Program and, of course, SciStarter for making this entire thing possible. And so with that, I guess I will say adios, everybody.
Thanks, Dr. Troy Hart. Thanks, everybody. See you next week. Bye.